Okay, so let's start. Welcome everybody to this special organic seminar. That is also an NCCR Catalysis seminar. I'm very pleased to welcome Professor Mark Lautens from the University of Toronto. As you may know, Professor Lautens has been a kind of guest in ESIC for the last 6 weeks. So he will still be with us until the end of next week. So if you want to meet him, don't hesitate to contact him and go to him to discuss. Let me just introduce shortly Mark. So this seminar is a little bit special. I asked him to be a little bit more broad picture about catalysis. And then next week, we will give a second seminar that will be more stronger focus on organic chemistry methodology. So Mark get educated in the University of Guelph. I have to tell, I even don't know where it is. So maybe you can explain us a bit. And then he moved to the group of Professor Barry Trost. At that time, it's Wisconsin-Madison, where he got his PhD in 1985. And then he moved to Howard University in a postdoc with Professor Dave Evans, what was perhaps the golden time of the Evans group. So he had the lab mate like Gregory Fu or Eric Carrera. So that's probably a very exciting time. Then he moved back to Canada, to the University of Toronto. And he liked it a lot at the University of Toronto. He made all his career at the University of Toronto, rising from assistant to associate for full professor at the University of Toronto. And there was also the opportunity to get several chairs sponsored by industry with other sponsors, like AstraZeneca Professor of Organic Synthesis, Merck Frost Industrial Research Chair, or the G. Brian Jones Distinguished Professorship. So Mark has a very fruitful career in organic chemistry, in catalysis, in different fields that has been recognized by several awards. So he's fellows of several Royal Societies. He get a very important award. I will maybe just name the very last one, the H.C. Brown Award of the American Chemical Society. So we are naturally very happy when he was interested to come to Switzerland to make his sabbatical year at the EPFL. Although we are not completely sure it was the ski attracting him or the quality of ESIC, but we are very happy to have you here, Mark, to speak about flipping the switch reversible catalytic reaction. Please, the stage is yours.
Merci, Jérôme. Thank you very much. And thank you to all of you who have made my visit very pleasant and very rewarding. So I thank all of the faculty who've taken very good care of me, made sure I was busy at lunch, and taken care of us in the evening sometime. So the lecture today is a little bit different. As Jérôme said, he asked me explicitly to maybe try to make it a little more general and about catalysis. So you'll see it's a little unusual, and maybe, hopefully, you'll enjoy it. So, whoops, except it's this better move, which it is not. Oh, there we go. Okay. Now we got to go back. All right. So if we think about synthesis and catalysis, of course, what we normally think about is we have a starting material and we go to a product. And typically, at least in catalysis, we're using some metal with a ligand, and there's some other reagent where we're going to swap X for Y. Although, of course, all reactions have at least the potential to be reversible, most of the time we focus on going from the left to the right. But what happens if we want to change it up and go from the right to the left? What happens if we want to go from a product back to some starting material or a slight variation of the starting material? So we have to think about reversible reactions and how we can make them reversible. And given we're in Switzerland, I asked my student to help me make a little graphic of our stay. So here I am in Lausanne. As Jérôme implied, perhaps I'm not always in Lausanne. Occasionally, I'm in the Valais. And there's some energy barrier to go from one to the other. You know, one has to use some energy to go up the hill, and then I managed to, this is not a picture of me, but a wish of me. So how do we go back if we're already here in the Valais and we want to go back to Lausanne? So currently our methods are a bit limited. It takes quite a bit of energy to go back up the hill, but maybe instead what would happen if we found some new tools that offered a new path into reversibility. So that's really what we want to think about. How can we go back from products towards starting materials? And if we were to look at a simple reaction diagram, I guess the question is, can we change the conditions? Can we change the ligands? How can we leverage some kind of strain to go from products back to starting material? So there's a couple of ways to think about it. One is to go back to some intermediate and then perhaps a modified product. And the other is to maybe choose a completely different pathway, but from product to some other material that we're interested in. So let's put some chemistry to the pictures. This is a reaction we became interested in 1997, when Marta Catalani first reported this reaction. And our interest really was how to make this a useful reaction in organic synthesis. Now, the mechanism has been looked at in great detail and was proposed by Marta in this first paper. And essentially, it involves palladium inserting into a CX bond. And then one of the key ingredients is the presence of norbornene. And that undergoes a carbopalladation or an insertion into this carbon-palladium bond. Now, that in itself is pretty much a one-way street, except at some point through the agency of base and then an alkyl halide, we can functionalize this ortho or ortho prime, either of these positions, depending on what the starting material looks like. And eventually, we end up with this di-substituted species. And at this moment comes a key reaction, which is a beta carbon elimination. So the reaction which occurred at the beginning somehow reverses to regenerate norbornene. But the key element is this material is much more hindered than this one, and hence the reaction goes in reverse. So norbornene enters and exits through a similar kind of reaction through increasing steric strain. And this turned out to be something that we used now, 20 years later, when we looked at these domino reactions, which I'll speak about more next week. But in effect, if we take an aryl halide with a tether on it, we can do an insertion, we can do a second insertion, we can then do a CH functionalization to make this palladicycle. And then there's a couple of different ways to go based on ligand. If the ligand is tritibutylphosphine, this reductively eliminates and we can make this spirobenzocyclobutane. But if the ligand is different, then in fact, we can add an alkyl halide, and much like the Catalani reaction, we can functionalize that position, only no norbornene is present. So we insert again, just like the Catalani reaction, we oxidatively add and reductively eliminate, and now we've difunctionalized. And our goal, I should tell you, was to then have this palladium iodide reductively eliminate, but that isn't what happened. Instead, a beta carbon elimination occurred. So this group became so big that in fact, this palladium eliminated, generating this alkene aryl palladium, but those were in close proximity. It re-added, but in the opposite regioselectivity. And then that beta hydride eliminated to generate this benzofuran. And so again, in this case, we've reversed the carbopalladation because of the steric effects of changing this phenyl group to a ortho prime disubstituted phenyl group. Okay, let's take a look at one more reaction that is a reversible reaction. And that is, I just finished describing to you many examples where an aryl halide reacts with palladium to undergo an oxidative addition. And that reaction is pretty much always drawn going from, although I've got it on the wrong side of the equation, from starting material towards this intermediate. And John Hartwig in 2001 looked at this from a different perspective, which was to take the product of oxidative addition and ask how to go backwards, how to go back to that starting material. I think it goes without saying, synthetically, this is useless. We go from a very expensive palladium complex to a very cheap starting material. So this is the wrong way in terms of value added, but mechanistically it was very important. And there's a few things that he learned. So he initially had the orthotolulyl palladium aryl species. And when he added tri-T-butylphosphine, the reaction went to the right. And the presence of ortho substitution actually facilitated the reaction to the right. And furthermore, if he made the tri-T-butylphosphine complex, he could then take that with tri-T-butylphosphine and go back to the right and form carbon halogen bonds starting from the arrow palladium X. So that really was stimulation for us with a problem that we had. And then around about the same time, Steve Buchwald reported that if you used a non-coordinating counterion, that you could replace a carbon triflate bond with a carbon fluorine bond, again, through reductive elimination of a palladium-2 species bearing an aryl group and a halogen. So that's kind of the background. And then it takes you to the first paper that we published in this area. And essentially, we were trying to make these molecules. And this was based on some work we'd done for over many years, where we took these dibromoalkenes and tried to do difunctionalization, one through a CN coupling, so a Buchwald-Hartwig reaction. And then we tried to couple this trans carbon-bromine bond, and we succeeded. However, at one point, we wanted to not succeed with that second coupling and just get our hands on the bromide. And that turned out to be quite difficult. And the reason is the product is more reactive than the starting material. So any palladium that was in there inserted, and this was a dead end. And in fact, we tried very hard. Steve Newman tried very hard to solve this problem. And ultimately, he solved it through the Hartwig protocol, which is that if you use tri-T-butylphosphine, all of a sudden, this step becomes reversible. And so you can isolate this compound. And there's Steve, a contemporary picture of him. And here's just a few examples. And this was an example where it's not apparent that it is undergoing reversible oxidative addition, but in fact, through some additional phosphorus studies and so on, we could demonstrate that the product did, in fact, undergo oxidative addition, but when a very bulky electron-rich phosphine was present, that step was reversible. And so we just lost a little bit of the material as the insertion product. And so here's just a bunch of bromo-indoles that we could make. And you might say, why do people care? It turns out making these things is actually quite difficult because they're very reactive. And so a lot of the existing indole syntheses really don't work. Anyway, so based on that reaction and our realization that the Heck reaction essentially involves insertion of palladium into an RX bond and addition to an alkene, that whereas Heck reaction is sort of classical, and as you'll see next week, there's lots of anion capture chemistry going on. What really wasn't known was this, the simple, what we called carbohalogenation. So this was the first example just a year later, and you can see I'm going through this quickly because this is all old chemistry, but essentially this other ligand that Hartwig developed, which is even more bulky, was very good ligand, modest palladium loadings in order to generate the carboiodinated material. And I guess the key is that where here we start with an sp2 and we end up with an sp3. And just a little bit of study of the ligands. You can see the ligand really matters a lot. Traditional, even fairly bulky ligands don't work at all. Medium, and then the bulkiest seem to work the best. And the catalytic cycle is just this obvious one, although there's clearly more to it in detail in terms of all the steps. So in terms of if, since I worked with Trost, I'll use the word atom economic, but only once. So that all the atoms of the starting material appear in the product. And that's one of the definitions someone would use to describe efficiency. If you don't waste any of the atoms, of course, you still waste solvent and catalyst and everything else. So here's just a few examples to illustrate that we could make scaffolds that turn out to be relevant to the kind of structures that you find in natural products like this one. This is actually, there's a number of compounds developed by Boehringer Ingelheim that are in this general class that are anti-cancer agents and so on. Okay, let's look for another example of reversibility. Let's imagine we have multiple carbon halogen bonds in a molecule. We want to do one reaction. Let's suppose it's this reaction on the right, where we insert into this carbon iodine bond and then hopefully do some kind of chemistry, whether it was Heck chemistry, whatever it was. The problem is if you have multiple halogens in a molecule, especially if they both happen to be iodides, you have a problem with selectivity. Will this carbon iodine bond or will this carbon iodine bond react? Now, one way to solve that problem is to make the reaction reversible. If every time it makes a mistake and gives this material, the ligand allows it to reverse, then essentially mistakes are self-correcting. And only when it inserts into the carbon iodine bond, which can do another transformation, does this reaction proceed. And that's exactly what we achieved. Here's just a few examples. We played around a bit with the conditions. But in effect, we could have these diiodo allyl ethers and then carboiodinate one of the two carbon iodine bonds and leave the other one untouched. We could actually add a second acceptor and then couple this one as well. But I think it illustrates the point better if we take this diiodide and leave one of the iodines in place. And when we did detailed analysis, we were convinced that both carbon iodine bonds have equal reactivity. So it wasn't just we got lucky and that somehow, insertion or this directed, complexation, then directed the insertion. In fact, both carbon iodine bonds are equally reactive, but by making it reversible, only one appears to react. Okay, so that's basically the background to what I want to tell you about today. So here's the reaction we described. Now the reaction it was super exciting when we discovered it, but it wasn't without its flaws. One of the things that's problematic is the ligand. Everybody likes to talk about the cost of the metal, but in fact, in this case, the ligand probably exceeds the cost of the metal by quite a bit. And furthermore, we wanted to develop an enantioselective version of this reaction. And with the help of Merck, they screened about 250 ligands in their lab, their robot lab. And what they found out was they could get high EE and lousy yield, or high yield and lousy EE. There were no ligands in their library at that time. And this was up to around 2019, maybe, or something, 18, that were going to give us what we wanted. So subsequently, a group in China developed a ligand, which turns out to work very, very well. But at the time, this was an unsolved problem. And of course, that ligand in itself it turns out to be not that readily available. Anyway, we were kind of motivated by this work by Jacobson and Hiyama, who independently reported this kind of transcyanation. This is very much in the spirit of reversibility, because you insert into a carbon cyanide bond and then you reform a carbon cyanide bond. What was kind of nice, though, was that this was used nickel catalyst and a chiral ligand, and this worked really quite well. And if you're interested, there's a couple of papers down there at the bottom. So we said, I wonder if we can do a nickel catalyzed version of this reaction. And we reported that just a few years ago. And let me just walk you through a little bit of what we learned. Now, in a longer version of this talk, I'd tell you this was somewhat an accidental discovery, and I'm happy to tell you more about that. But we legitimately had wanted to do a nickel catalyzed version of this reaction. We spent about 5 years trying. And then when trying to make stoichiometric compounds, we actually discovered the reaction we've been looking for. So here's the conditions: bis triphenylphosphine, nickel diiodide, manganese, and toluene. And that gave us the same kind of iodo, in this case, carbon-carbon CI bond, so carboiodination. And this was scalable. Now, there's a few things about this reaction that are important. One is this carbonyl is important. It either needs to be here or it needs to be here. So somehow this group is maybe directing the nickel into this insertion step, but you need some kind of coordinating group in order to make this reaction work well. and Hyung Yoon and Austin Marchese, whose pictures you see here, are the ones who developed this. And you'll see all the examples have that carbonyl group. I don't have them on the slide, but I have the other examples where there was an amide group here. But the reaction works well whether you put substitution here, on the nitrogen, it all works just fine. What works less well is if the R group becomes very large, or it's not bad with alkyl groups, but very large starts to be a problem. All these reactions are a problem if you take away any substituent there, because it just does a Heck reaction. Ultimately, the Heck reaction is a faster and lower energy process than a carboiodination. Now, again, there's a long version of this story, but I'll give you the short version. We tried to do an enantioselective reaction and we got some success. Our success was that we could get up into the high 70s, around 80% enantiomeric excess. And we use nickel and manganese again. And this ratio is may seem very, very odd to you. It turns out it's important. So I had two students were working on this. One student took one enantiomer of BiNAP. The other student took the other enantiomer of BiNAP, and they each ran the reaction. One said the reaction works and gives 80% EE. The other said the reaction doesn't work. Of course, that's impossible. So we looked at the BiNAP, and one of them was oxidized about 10%. One of the phosphines of BiNAP was oxidized, and that turned out to be actually essential for the enantioselectivity. So that was an example of two people doing an experiment and something good coming from, not checking how good the BiNAP was. Anyway, this reaction works, but it's not great, I'll be honest. So we looked for another way, and that other way used a carbomoyl chloride. So let me talk you through that chemistry. And here's Austin, and a student from Germany, from Frank Glorius's group, came as a visiting student, Marco Wollenberg, and he assisted with this project. So nickel diiodide, again, a pretty cheap ligand by comparison, manganese, and we added potassium iodide for two reasons. One is the carbomoyl iodides are not very stable. The second is that the reductive elimination to form a carbon-bromine bond is not that great. So we needed iodide, but we couldn't put it in our starting material. So we had to add it exogenous. But what was really nice, so in this case, of course, you're inserting into this group, adding to this pi system, and then reductively eliminating. The nice thing about this was a chiral ligand suddenly worked very, very well. And so you can see the kind of examples, an alkyl group, alkyl, alkyl. We got good enantioselectivities for the first time, really. And so we're using a cheap metal, cheaper ligand and relatively simple reaction conditions. Okay, here's another story that unfolded in an interesting way. So way back in 2014, Dave Petroni was looking at what happens if we have a pre-existing stereocenter and we make a new stereocenter. Since we had so much problems getting enantioselective reactions back at that time, we asked the question, what happens if there's an existing stereocenter? Will there be any diastereoselectivity? And the good news is there was. So 2014, we get the SYN. So of course, Austin came along and said, well, if it works with palladium, let's do it with nickel. We'll show that it's a cheap way to make these compounds. But much to our surprise, the other diastereomer was formed, and we don't know why. We have tried to play around to understand this, but the bottom line is we don't know. But I guess this is sort of making, what's it, orange juice out of, or lemons on a lemonade out of lemons. So we got a different diastereomer, and that was kind of good because that gives you access to both. But then I think there was something much more interesting happened. We did a third experiment. And the third experiment was what happens if we take a cheap palladium, like a tetrakis, instead of the QFOS? What happens in that case? That is not going to do carboiodination because with this ligand, you can't do the final reductive elimination. You need this huge ligand in order to drive the final CI bond formation. So it does a carbopalladation and then a CH insertion and functionalization. Well, now that was kind of interesting. And then Austin, I think, did a very important experiment. Well, he said, well, can I take this material and turn it into that if I just change the ligand? So I go from QFOS to tetrakis. But he did one more experiment than that. He said, well, if I take this other one, maybe it'll bite in, and instead of making the cis, it'll make the trans. That turned out to not be the case. And that opened a door to something much more interesting mechanistically, which is that whether we started with the anti or the syn compound, we ended up with the same material. So how on earth had that happened? So that was the surprise. That was the surprise, but good news. And the hypothesis that we put forward was that maybe there was a beta carbon elimination. And so this reaction is not so sterically hindered. And so it became a kind of a test case for understanding something about this beta carbon elimination. So let me walk you through what experiments we did. So we looked at sort of how far along the reaction path, right? And the furthest is the anti, the closest is the syn, and the starting material is kind of along the way. So the anti gave us 45% yield. We got an X-ray structure, and the other major product was the proto-dehalogenation. You can see it's about 1:1. If we went back to starting material, we did better. We got about 10% more yield and much less of the proto-dehalogenated compound. And of course, maybe not surprisingly, if we started with the one that was even further towards the final product, we got a very much improved yield and none of this. So that kind of makes sense, more or less, that this one somehow has to get turned back into this one before it can go on to this one. And so it has the longest path, and for whatever reason, various other things can happen, including this, that kind of eat into the synthetic utility. So here's our questions. The starting point for, say, the anti was going to be insertion. And then what we'd originally wondered was just CH activation, and then we'd make this. That turns out to not be observed. And we did a ton of computational computational work. Bijan Marabi in my group is the person who knows far more about that than me. And this material is quite a bit higher energy than the one that we actually made. So we thought that maybe it's beta carbon elimination, but then the palladium has to move from one side of the pi bond to the other, recarbopalladate or reinsert, and now it can do the CH functionalization, generate this palladicycle, and go on to product. But we couldn't completely dismiss a couple of other mechanisms. One is maybe the palladium hops from one methyl to the other, and the other is maybe this center epimerizes. We thought that was not so likely, but we wanted to see if we could be sure. So that's not happening. What about these two? Well, what we did was we replaced the methyl with an ethyl, and we thought if the palladium shifts, we'll now make this secondary palladium. That has a couple of things that it might do. One is that it could cyclize. We doubted that that would happen. What we expected was there'd be a beta elimination. So if the palladium hops, we expected that might be the outcome. Ultimately, we took this material and the syn and the anti, subjected each of them, and we got the product. Now, one thing that sort of was a bonus of trying this experiment was that before the anti-product only gave us 45% yield when this was a methyl. And when it was an ethyl, it was 73% yield. So the bigger this group turned out to be far better from a synthetic point of view. But in no case were either of these materials formed. So that seemed to, in our view, rule out the likelihood of this palladium shift. But what about the epimerization? So the way we tested that was a bit different. We said, well, if we start with an enantiomeric material, we'll get one product, one diastereomer, but the enantiomeric ratio of this started off at 99.5 to 0.05. So that's exactly what we got. Now, what happens if we start with the anti-material? Well, if this one epimerizes, then we'd actually get the enantiomer from this, and that would be interesting and tell us that this group was changing. But in fact, it gave us exactly the same enantiomer as what we'd started with before. So that's not happening. There's no epimerization here. We didn't think it was likely, but then again, it's allylic and benzylic. And so we thought maybe we should just be sure. So this is not happening. That's not happening. We're pretty confident this is the pathway that's going on and based on the computational work. So as I said, this group here makes a difference. And so if we took a mixture of 1-to-1 cis to trans, and we tried it with, say here, R equals to methyl, we got a strong diastereoselectivity, a pretty modest yield. We could increase the yield if we started, sorry, we decrease the yield if we only started from the trans or anti material. If we replace that methyl with an ethyl, as I implied, the yield jumps way up, and that is true whether we have other halogens in the molecule or electron withdrawing groups. And so the chemical yield gets better. The diastereoselectivity is always essentially one diastereomer, and that proved to be kind of interesting. And we took a kind of this is a silly experiment, I must say. We just took as bad a mixture as we could come up with, right? If we had all three materials in there, what happens? Well, they all converge on one single product. So from a mixture of three things comes out one product due to this reversibility of the C-C bond formation. Okay. I'm going to take you now to sort of the most current things that we're doing. And that is based on some work by Gevorgian. So Gevorgian has shown that if you take palladium and blue LEDs, that there's an interaction of a kind still, I would say, to be determined, but it involves activation of the palladium in some way. And his proposal in this paper in 2018 was that a more energetic palladium species essentially abstracts the iodine, makes a palladium 1 and a radical. That abstracts a hydrogen that's 1,5, generates a new radical, which is an alkyl radical instead of a vinyl radical. That alkyl radical cyclizes, and now this recaptures the iodine. So he's done a kind of a carboiodination, but through this movement of hydrogen atoms and ultimately movement of the iodide. So that's quite an interesting paper. And my students who'd taken a look at it thought, well, what could we do a carboiodination with blue light? So I don't have a lot of experience with this. This was a good, fun learning experience for me. But one of the advantages might be that milder conditions. So instead of heating with a very expensive, bulky ligand, maybe we could get away with something easier. And that's exactly what I'll tell you about now. There's Austin again. He's been a busy fellow. It comes down to basically this. We could use a palladium-2 complex, this DPE phospho structure I'll show you in a minute. And what are the key things? So a relatively cheap ligand and room temperature. So instead of heating with a complex, expensive ligand, we could do something much easier. But there was even a bigger bonus that there were other potential interfering elements like pyridines, free anilines, carboxylic acids, and phenols. And here's another pyridine. And all of those were stable under these blue light conditions. Whereas before, each of these groups caused some issues when we tried to do traditional carbopalladation or carboiodination, I should say. So that just appeared very late last year. So I'll tell you a little bit more about this to try to get a handle on what's going on in terms of the carbon-iodine bond formation. So the group of Tong, just after we first reported the carbohalogenation, reported their own version of a carbohalogenation, only it was on a vinyl iodide and an alkene. So they made these kind of species. So that's from their paper a few months after ours in 2011. Now, one of the experiments that they did, which actually Steve was just in the process of getting ready to do, was to put a deuterium here so that we could learn about the diastereoselectivity of the carboiodination. So Tong had already done the experiment. There was no need for us to do it, but here's basically what he learned. He put the deuterium cis to the tether, and if it's a palladium-2 reaction, it inserts, it carbopalladates, and then it reductively eliminates, And so he's only got 75% deuterium incorporation, but there should be high diastereoselectivity. There's a stereocenter here. There's now a stereocenter here. So from 75% of one isomer, he got a single diastereomer with 75% deuterium incorporation. So that's what a 2-electron process looks like. An oxidative addition, insertion, reduction. That's the bottom line. So deuterium scrambling suggests 1 electron, no deuterium, but this is at short times, I should say. Eventually, this does start to equilibrate either through iodide attack or palladium attack here. It gradually deteriorates, but it starts off quite good, as you can see, 75-0. So here's the experiments we set out to do. We took a material, we weren't even as good as him. We only got 65% deuterium incorporation, but that's what we had, so that's what we used. We did the palladium DPE phos with blue LEDs. So a 2-electron process, we expect 65-0. A 1-electron process, we expect 1-to-1. There's our radical, which we figured then would be attacked from either side or attack from either side, forming the carbon-iodine bond. So what happened? We took our 65% deuterium and we got exactly 1-to-1. So that implies that there's a radical here. But it doesn't tell us that the reaction was a radical cyclization. It just tells us that at some point there's a radical here. So we had to set out and see if we could make sense of that. That's the radical. So we made the compound that is mostly 1 diastereomer. And we made that by our palladium 0 with a bulky ligand, right? Because that's a highly selective reaction. So it was 8.5-to-1 diastereomeric ratio made by a palladium 0, no LED. If we took this material and treated it with palladium, nothing happened. And that conditions A essentially mean this DPE phos. So no LEDs, nothing happens. Kind of boring. If we have DPEs, but no palladium with blue LED, nothing happens. Here's no palladium, but triphenylphosphine. So either ligand, nothing happens, more or less. But the minute that we take this product and subject it to the palladium with blue LEDs, it's immediately 1-to-1. So that tells us that the product is not stable under the reaction conditions. And obviously, we can't use this 1-to-1 result that I just told you about as evidence of a radical cyclization. It's only evidence that the product wouldn't survive in terms of stereochemically survive. So then we tried to do some stoichiometric experiments. We took this iodide with palladium and DPE phos, no LEDs. This makes a complex, which try as we might, we could not crystallize, but we could see it by mass spec. And if we took that material and shone blue light on it, we got the iodide. So the oxidative addition can happen without blue LEDs. The carbopalladation can happen without blue LEDs, but not the final reductive elimination. There's DPE phos for anybody who was wondering. Okay, where we could make a complex was with triphenylphosphine. That's actually much better. And that's easy to make by taking this stuff with tetrakis and you get this material. And that's the trans diphosphine. And that compound, if we treat it with no blue LEDs, heat it, do whatever we want, that does not reductively eliminate. So essentially nothing happens. That is a stable complex. On the other hand, if we take it with blue LEDs, we immediately get the iodide. And whether we have it just with triphenylphosphine, that's no DPE phos, with DPE phos, with or without potassium carbonate, more or less within, let's call it broad experimental error, we get the same product. So this tells us a couple of things that are important. One is that the first steps do not require LEDs, but the final reductive elimination does. And furthermore, the integrity of that carbon palladium bond is highly questionable under blue LEDs. So what can we say? Well, Gevorgian suggests that the palladium is activated by blue LEDs. It could abstract the iodide to make this aryl radical, which would certainly cyclize. But we also know that palladium on its own can oxidatively add. And this, we believe, of course, would cyclize, give us 5-exo trig. This one we know cyclizes because we made that material and isolated it. And then our experiments tell us that this is a blue light mediated process where we can cleave that palladium to carbon bond and generate the radical. And we know that the product is also reversible. That is, this can go back into this manifold to B and then go on to product. Okay, I'm just about done. Now some unpublished work that kind of relates to this same topic. Now, this is not a synthetically useful reaction. As when Nikolai came in to see me one day and he saw them on my screen, said, "This is," you can imagine, in his charming way, what the hell are you doing this for? So the question really is this. Imagine you have a stereochemical center with a carbon iodine bond, and suppose you want to make the other isomer, an enantiomer in this case, but it could otherwise be an isomer. So now everybody likes this term editing. So my students now are starting to use that term. I apologize. So what kind of editing could we do? Well, way back, Steve Newman did this experiment. He took an aryl iodide and a strained alkene and did a carboiodination. Now, again, that wasn't very interesting in 2011. I'm not sure if it's more interesting in 2023. But he did it with this this very hindered phosphine. And so he generated this compound. And we had trouble finding other alkenes that you could do an intermolecular carbohalogenation. So that's why we were kind of stuck with it. But the question that we started to ask ourselves was, well, if carbon iodine bonds are labile under palladium and blue LED, could we make this compound? And that's what I'm going to show you in the last few minutes. And our idea was this, and it really follows what I've just told you about our carboiodination. If palladium is excited by blue light, then maybe it can interact with the syn compound. It could just do an oxidative addition, but maybe it fractures that bond and makes the radical. And if it makes the radical and some palladium-1 complex, maybe this can form the anti-product. And so this compound is not really accessible using any chemistry that's out there to date. So that became kind of our study. And this is just a summary of what we've learned so far. So we're a bit limited. We're limited by how good the original reaction that Newman discovered was, which is the aryl iodination of that alkene. So if we can't make starting material, you could say we can't really test the starting material's integrity. So they made a bunch of them. Here's the products that arise from it. Took it with palladium, with DPP pen, toluene room temperature with blue LEDs, and made the trans isomer. And you can see whether it's electron poor, electron richer, halogen containing, even something with an iodide, although the yield is much better, worse. You can generate this trans isomer. Now, one of the questions that Nikolai asked me when he came in was, so why don't you just displace this with an SN2 with iodide and do a Finkelstein type of reaction, right? So I immediately sent a note back to the group. Do you guys do that experiment? And they tried every condition they could. And this reaction actually doesn't work if you just add iodide. So thank you, Nikolai, for that, challenging that point. Okay, so here's a compound with a phenyl. If we make this, too big, then let's say it looks like it's degraded, but that's wrong, right? It looks like this is less selective. What you could really say is this bond is less reactive. And so, of course, in the simplest case, it fully reacts. in the bulkier cases, it's slow to react. So this isn't that these are less selective, it's that the starting material is slower to be consumed. All right. In contrast, if we make this small, then the reaction actually is less selective. So the smaller the group is, the lower the exo, endo, or whatever you want to call it. Here's one that actually ended up rearranging on us. And so these are decreasing steric bulk lowers the selectivity, but larger groups actually more have an effect on whether the reaction even happens. We did a little bit of computational chemistry. There's Bijan again. First thing he did was he just looked at what happens if this is an H. And you can see that, you know, this is higher in energy than this, which makes sense, right? Exo is usually lower in energy than endo. And then when he put these groups on, at least while the numbers are not right, the trend is correct. A phenyl is better than an alkynyl in terms of exo and endo selectivity. A few control experiments, and then I'll be done. We took the carbopallidated species with the triphenylphosphine on it. They got an X-ray structure of that. They heated it in toluene with no LEDs, and essentially they get no reductive elimination, not much of anything else. With blue LEDs, immediately we form the anti-compound. So although that's the exosyn, this gives the anti-endo iodide. And just some data in terms of as you put phosphines and so on. But essentially, you don't see any of the exo-iodide, you only see the endo-iodide. Then we took this and complex, similar to this, but only the phenyl compound, and asked, is it a catalyst? Is it a viable catalytic species? And the answer is yes. Now, we only got about 4 turnovers, but this material not only can reductively eliminate to give this material, but it can also catalyze this material turning into this. But after this amount of time, this isn't a great catalyst. And so some of it is left behind. So that is unreacted starting material. This goes to this, and some of this goes to that as well. I think that's, oh, one last thing. We tried to do the bromide. We got hopeful results. It's about 20% yield, a little bit of the exo, and a little bit of alkene. So again, when it gets to the endo position, there's a hydrogen there, so it can actually beta eliminate, right? So when it's on the exo face, you're fine. When it's on the endo face, there's a hydrogen nearby. That's where the alkene can come from. Well, we're at the end of the story. What did we learn? I mean, we got very interested in making carbon halogen bonds, and it turns out if by playing with the ligand, by playing with the metal, by playing with the presence of light, we can reversibly react carbon halogen bonds and access novel structures through that method. We can also break and remake carbon-carbon bonds, and that's a harder thing to do. And they go through some kind of common intermediate, whether it's a Catalani reaction, which I really didn't talk much about, or whether it's some other species. As you change the ligand, you can suddenly access carbon-carbon bond cleavage reaction. And sometimes, you know, we may get a kinetic product from the, or even arising from based on the mechanism. It's the higher energy species through one kind of palladium reaction. If we change the reaction conditions, then we can access the thermodynamic one. And so that is the end of my story. This is a picture. Finally, we were together in person. The lockdown was more severe, I would say, in Canada than it was here. So this is some of the group of folks who participated in this study, and this is the more what we endured for a while is Zoom group meetings. And so I thank all of those people. You've seen their names as we went along. Austin, Bijan were particularly crucial in this, many of these studies, and in the early days, Steve Newman. These are the folks who funded us. And I thank you all very much for your attention and for the chance to spend some time at EPFL.
Thank you, Mark, for the nice presentation on reversible catalysis. Are there questions? So people on the Zoom can also indicate their questions. Let's start with the audience.
I asked you a lot of questions.
I was like intrigued by that nickel chemistry. We had a ton of manganese inside. Was it just to get an initial
Right.
zero? Was
That's
that-
right.
was
That's
that
all
a
it's for.
trick?
No, that's all it's for. And in fact, we did better than that, although I don't have them on slides, that ultimately we found that if we, where is it now? I'm going to zoom back a bit. We ultimately found that you could use triisopropyl phosphite and avoid manganese altogether. So that's a much milder conditions than the ones that we had originally developed. There we go, finally.
Here what it was right now.
So here you're using, there's not a ton of it in this case, but in a number of examples, we
Yeah, it
could
was
use
to
triisopropyl.
absorb
Yeah,
some-
at the beginning, part of that is just us learning, right? So this wasn't so much, but maybe the first, I can't remember if there was a moment now. I think it's not bad. 0.6 equivalent. So, I mean, that's an excess compared to 10 mole percent for sure. But as I say, we could also use triisopropyl phosphite, and that turned out to be even better
As the reducing agent.
as a reducing agent, which was really good because one of the substrate classes we did was a dearomative reaction, and the product was a secondary benzylic iodide, and that was super sensitive. And so it did not tolerate manganese, but triisopropyl phosphite, it did tolerate, and so it could.
The general that that.
Well, we looked around and there was, I think, one example somewhere in the literature of people using it, but it's not very widely used. For us, it's worked in a number of cases, and the students seem to kind of go back and forth on which one they use.
So the manganese all depends on the size.
Right, the particles, where you buy it from, and all this kind of stuff, right? So I keep wanting them to use triisopropyl phosphite, but in some cases, and I guess the case that's most relevant, is the one right here. Here, of course, we don't want to use triisopropyl phosphite to reduce this because otherwise it'll mess up the asymmetric reaction. So that's the only problem. If you're trying to do an asymmetric reaction, you don't really want to throw in triisopropyl phosphite and potentially be a ligand that's going to give you a background racemic reaction.
Oh, so it does. can be-
Yeah, I mean, I think it's a ligand, but it's not as good a ligand as the other one. But, if it erodes it by 10%, that's already 10% too much. So then we just use manganese.
Yeah, so my first question, you said that it's difficult to do this carbon bromine forming reductive elimination.
Yes.
So put carbon iodide in there, and it's kind of counterintuitive, because carbon bromide bond is stronger than carbon
Right.
iodide.
Yes, so it's not so much the stability of the product as the energy barrier to get over the top. So when we first started working on this, we worked with Ken Houck, and he did some computational work, and sure enough, the energy for the reductive elimination is the problem. It's not the stability of the product, it's the energy barrier.
So it's much higher.
It's higher, and then chlorine higher still. So we, in general, that's a unsolved problem, is designing a system that will do carbochlorination, carbobromination. That's tricky. You can start with an aryl bromide. So if I go back, if you start with an aryl bromide, that works because you can add potassium iodide, but that still means that the final reductive elimination is a carbon iodine bond. So it isn't the insertion that's the problem, it's the reduction, right? Because most of these ligands, especially for palladium, say, we just go back to palladium, these ligands are really good for carbon chlorine and carbon bromine insertion. They were designed for that purpose.
Yes.
So the insertion step is no problem, neither is the insertion into the pi bond. The problem is the final reductive elimination. And that just is a higher barrier. Well, because one of the things Houck showed, and maybe I think I stuck at the very end of the talk, I have a picture of what Houck did. Oops, so there's the higher barrier for these two. One of the things that Hauck showed, and it's related to Hartwig's work, is the key to the reductive elimination is having only one ligand on the palladium. So otherwise, if you have two ligands, then the reduction is not so good. But if you take a bulky ligand, which is then makes it monoligated, then this pathway happens. And the problem with small ligands is they form the trans complex, and that's dead. I mean, that's basically the complex we made. And we couldn't get that to reductively eliminate unless we shone blue light on it. And then it reductively eliminated. But on its own, first it's trans, but on top of that, these relatively small ligands do not help the reductive elimination. If you have something really big, it seems to help. The other problem, as how looked at in this paper, was, as you get really big ligands, then all of a sudden the carbopalladation does get harder and harder, right? So the bigger the ligand, the more it affects the second step in the catalytic cycle. So you have to kind of worry about that, which is why we have not been able to have a substituent on here, like and do a secondary, except when it's a de-aromative reaction. So that's a challenge. That this step becomes a problem if it becomes a tri-substituted double bond.
Plugins do better.
We tried some carbines, but we haven't really explored that very fully. So I don't know the answer.
It was more difficult to actually get two of those bulky carbons there.
Yes. Yeah. It's a good idea. One of the things that we did actually early on. So Steve Newman went to Frank Glorious for like a 6-month or 4-month stay right at the very end of his PhD. And that was because Frank had made some super bulky chiral NHCs, which he had, I think, coordinated to rhodium. So Steve tried those and none of them worked at all. But, it was a very limited set. It was just what Frank's little group of things had made.
So if an activation aniline, really the key factor and the reductive elimination is kind of productive intermediate step, 27 kilocalorie. If you heat it up a little bit, it can go uphill, right?
Yeah, I mean, I guess you imagine there's a way, and we have a paper that I didn't talk about where we do hydrohalogenation, and that one we could get chlorine and bromine, but they were vinyl, not alkyl. So that's the other thing. If you can make it a vinyl reduction, sp2, then that seems to be easier. Mm-hmm. So, let's say we're close, right? I mean, this reaction, the reason it probably wasn't, discovered or reported much in the past was because it was very ligand dependent. And so people just didn't see it because those kinds of ligands were more or less recent inventions, right? So it's hard to do with just triphenylphosphine or regular alkyl aryl phosphines.
Another question that this is divergence between palladium and nickel catalysis. And the argument is that when you have trans, the 6 amendment further cycle cannot be formed, it's difficult to form, then you do ritual carbopalladation. Is that right?
So
why does, trans 6 memory should it be okay?
Yeah, I mean,
that's a strand.
Right. So anyway, these are some of Bijan's calculations from this Nature Chemistry paper. But this material here, I think it was, so this is the energetic landscape that he calculated, and it's not that it seems impossible, but the retrocarbopalladation is actually turns out to be better. Let me just see if I've got one before. Okay, let's see this one. This one is for starting with the anti, and then it complexes to the aryl, beta eliminates, switches from one face of the alkene to the other, carbopalladates, complexes the carboxylate, activates the CH bond, and reductively eliminates. So that's minus 27. And then I think the other one was minus 20.
But you have to look at the beta cycle, the stability.
Right. So right. So yeah, I realize. So that's one part, is what is the energy of, but then there's also this, right? So that was, let's see now. So starting from That's the anti. And then that's the energy barrier here is 35. And the other one was, let's make sure I'm going the right way, wrong way. The other one is yeah, for sure.
Yeah.
Sorry, I don't have them all on one page. But I have the paper if you want to take a look at it afterwards. So yeah, I mean, we expected to form the trans, but it didn't. And then when we looked, it looked like the energetics were such that this cyclization here was much lower. But I appreciate, what you're saying is, of course, it's the barriers that matter, right? Yeah. Something different.
You never showed it, but like what actually is a synthetic kind of potency of this neopentyl iodide? Do they still undergo kind of typical what we know alkyl iodide?
Right. So you can displace with cyanide, you can displace with thiolate, you can do Suzuki couplings on them. So there's stuff you can do with them. But of course, one of the things that I remember saying to one of my students was, if you're going to displace with cyanide, then why not just do the Jacobson and Hiyama reaction or like, Bill Morandi has done, right? So you could obviously do a kind of transfer reaction. So this fits into a kind of a transfer reaction manifold.
Can you exploit further that radical?
Yeah, that's to be determined, right? That's really something very new. So we're trying to figure out what can we do with that radical if through the palladium LED manifold. Absolutely.
So maybe I said two questions on this radical one. So the first one is how does it change the energy of the reductive elimination? Could you just show one example where you could do a little bit of the bromine?
Right.
But it doesn't look like it's much better.
Yeah, I mean, that's right. At the moment, this is sort of all we've got because you can't do this reaction. The problem again is how do you get the starting material, right? So if you can't make the bromide through a carbobromination, how do you make it? So this is just the carbopalladation. That step works, but the reduction to form this bond is tough. So it's hard to make that starting material to test this concept. This is the best we've got, and we know those yields from stoichiometric material are lower than the synthetic yields. So yeah, I mean, it's an important question. How can we start to maybe take bromides and see if we could do chemistry? So we're trying to do this in systems that aren't so biased. If you just had an alkyl bromide, but you maybe had a coordinating group, could you invert the carbon bromine bond if somehow there's some interaction after the inversion step? So that's what we're trying to play around with. Because I mean, this is not synthetically useful. This is not the point of this really at all.
No, my second question was, what if you have a less biased system, but you put a chiral ligand in palladium? Will it be able to recognize the phase?
Yeah, that we have not tried yet, but we've talked about that. So yeah, that would be very, very interesting. In the case that that we first developed, it's kind of useless because the stereochemistry step has already happened. Where are we? Yeah. So once you've made that carbon-carbon bond, there's no stereochemistry, right? So you're kind of doomed. So that's more about, and I have to say, I believe that the first step of it is this one. And the reason I say that is because if you look at Gevorgian's work, and I only thought about this actually during one of the Zoom calls with my students while I was here, was if you look at what Gevorgian did, where are you? There you are. He doesn't have a substituent here. So he could have done a beta hydride elimination, but he doesn't get that. So I think what happens is once you form this species, it doesn't beta hydride eliminate. And so I think in our case, the fact that we still need an R group right there says that most likely it's a carbopalladation and there is a real live palladium bond there that could beta hydride eliminate. So that's a working hypothesis. We don't have any proof of that. But I think if we look carefully at what Gevorgian did, it says that our chemistry probably is carbopalladation and then this. That's my guess.
Maybe you could test it with your deuterated system. There you could see.
Yeah, I mean, we also, I guess that's the other question is if you made the complex with if you could just put a hydrogen there, you might be able to test, if you could make this complex. I don't know if that's makeable or whether it just beta hydride eliminates. I fear it does. Yeah, we thought about putting a silicon there and then maybe you could desilate. Anyway, that's really speculation, but just based on what Gevorgian saw, he forms a 5-membered ring and he doesn't beta hydride eliminate. So I'm shocked, in a way that that's the product that came out. And I think it attests to the fact that because he's doing a hydrogen atom transfer, he has a radical cyclization, not a carbopalladation.